Okay, hi there, Vic. Let's say we are trying to find the dimensions of the largest rectangle, which you can inscribe in the curve y equals 36 minus x squared. And in order to get started, how about we inscribe any old rectangle? How about to get started first, we make sure, convince yourself that the right edge of this curve is at 6, 0, and it has a similar point at -6, 0, and the apex of the parabola is at 0, 36. If we let x equal 2, and we inscribe a rectangle, well, when x is equal to 2, y will be 2 squared is 4. 36 minus 4 is 32. So this corner is at 2, 32. Which means the area of this rectangle will be length times width. The length of the inscribed rectangle is 4, and the width is 32, and 4 times 32 is 128. If we create a different rectangle, how about if we let x be equal to 5, and we go up and we inscribe a different rectangle. The area of this long rectangle, of course, will be length times width. The length will be 5 and 5, or 10. If we let x be equal to 5, 36 minus 5 squared is 11. This point would be at 5, 11. And the area of the rectangle would be 10 times 11, or 110. And the whole point of this problem is to find the rectangle which has the largest area. Hopefully it'll be more than 128, and it'll be less than 110. Now, instead of picking a particular rectangle, let's pick a general rectangle. We'll have the upper right-hand corner of the rectangle be x, y. The area of the rectangle can be described as a function of x and y. The width is 2x. The height is y, which makes the area of the rectangle in terms of x and y as 2xy. These optimization problems are called constrained optimization problems because the upper right-hand corner of the rectangle is constrained by the curve y equals 36 minus x squared. And we are able to write this area function not in terms of two variables, but in terms of one variable. And the area of the inscribed rectangle can be written strictly in terms of one variable by noting that y is equal to 36 minus x squared. So this point can also is x, y, but it is also x, 36 minus x squared. So the area of the inscribed rectangle is 2x times 36 minus x squared. And make sure that's in parentheses, please. if we distribute the 2x, 36 times 2 is 72, so this becomes 72x minus 2x cubed. And there you go, there is our area function. In order to find the maximum or the minimum of the area function, you take the derivative, set it to 0, gobble, 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 which makes the derivative of the area function 72 minus 6x squared. If we set this to 0 and divide through by 6, you get 72 over 6 minus x squared equals 0. And then, oops, I spelled 72 wrong. And then x squared is equal to the square root of 72 over 6. X is equal to the square, and it's actually equal to plus or minus the square root of 72 over 6. And 72 over 6, they both share a common factor. Well, 6 goes into 72, 12 times. So x is equal to plus or minus the square root of 12. And perhaps your teacher wants that in simplest radical form, so that would be plus or minus 2 root 3. So, find the dimensions of the largest inscribed rectangle. We have x. To get the y coordinate, we plug in, we'll write y is equal to 36 minus x squared, or y is equal to 36 minus the square root of 12 squared, which makes y equal to 36 minus 12, or y equals, what is that, 24. Okay, so the dimensions are, so if this is 2 root 12, the entire length of the rectangle is 4 root 12, so the dimensions are 2 root 3. 4 root 3 by 24. Oops. And the dimensions are 4 root 3 by 24.